Now that we've learned what the SI standard units are, and again, if you look at the screen, on the left-hand side is a small table with the 7 SI standard/base units. These are the units that the International Bureau of Weights and Measures has actually come up with a physical, natural phenomenon, or in the case of the kilogram, an object that means that unit. All things in the world are referred back, when you measure them, are referred back to these 7 units. Well, we all know that there's a lot more units in this world than those 7. The other units that we have in the metric system are what we call derived units. They are derived from those 7 base units. They are combinations of those 7 base units. In some cases, the combinations are quite complex, so we come up with a new unit. Looking at the screen on the right-hand side, you see a second table called Common Derived Units. I've selected just 7 of the more common derived units that we use in chemistry. You will use a lot more in physics. The first one is area. For math class, everyone knows that to find area, you multiply a length times the width. Now, if you were measuring the length and the width of something, in metric, it would be meters for length and meters for width, so that when you do the math, it comes out to be a meter squared. There is no physical, natural phenomenon that we call a meter squared like we do the kilogram, the piece of metal in France. But we do have a meter, so when we say meter squared, I am combining my definition of a meter in one direction in conjunction with the definition of meter in a second direction, and that becomes a meter squared. We have an idea, it's derived. Then we have volume, kind of the same thing here as area. If you have a length times a width times a height, then you have meters times meters times meters, you get the meters cubed. One of the most common units we use in chemistry is the one for density. Hopefully you know by now from middle school that density, remember I used the symbol rho in my class, density is equal to mass divided by volume. So in terms of units, mass is SI kilogram and volume is SI meter cubed, as we just discussed. So now that becomes a combination unit, combined from the SI mass and the SI volume, and we now have a derived unit for density, a kilogram per meter cubed. I'm going to assume that most of you have worked speed or velocity problems either in your math classes or in your middle school science courses. We'll just briefly mention that speed is distance divided by time, so we have a meters divided by seconds. Those two SI base units come together to form a pretty simple derived unit. But below that, I will show you some of the more complex, and these are still pretty straightforward and not too bad, complex derived units that we use. Force is a very common one in science. Force, if you look at the formula, I hope most of you have seen this before, is mass times the acceleration of an object. You might have seen this in middle school. The SI unit for mass is going to be the kilogram, and the SI unit for acceleration is meter divided by second squared, or meter per second per second. So when you combine these and you do the math, this becomes the derived unit. And now, force is just in terms of SI mass, SI length, and SI time, and it's pretty clunky. You don't want to really write that a lot. So what we have been able to do to overcome that is to come up with new units that we call derived units that equal this monstrosity. For force, the new unit that we have is called the Newton, named after Isaac Newton, and we automatically know that the Newton is equal to a kilogram times meter per second squared and is itself then standardized. Then we have the SI, the quantity pressure. We do use pressure quite a bit. The SI unit for pressure is called the Pascal. Pressure is calculated by force, taking a force of an object divided by the area on which it acts. So when we simplified, I should have put area right here. So when we simplify this down into units, we have that Newton, which is kilograms times meter per second squared, divided by another meter squared, so kilograms times meter per second squared divided by another meter squared. We can see that the meter on top cancels, and so does the exponent here. And if you look in the box, you'll see that's what I have simplified it down to. Again, that's very clunky. No one wants to write that. So that derived unit is given another name, an equivalence, and we call it the Pascal. The final one, I'm not going to do the math on the board, but is for energy. Energy is calculated in many ways. That's one reason I'm not going to show it. There's a lot of ways to calculate this and come up with this, and there's a lot of equivalencies. But just one way to do it is by taking the mass times the velocity squared unit. So you get a kilogram times meter squared divided by second squared. And that simplifies down to a joule. I want to just quickly work through two examples of converting when we have these derived units. In the first example, we have Tom driving at 75 miles per hour. So 75 miles in 1 hour. The trick to converting derived units is that you can't deal with both units at the same time. So for example, this 75 miles per hour, that is a distance in the mile part of it and a time in the bottom. You can't convert distance and time at the same time, no pun intended. So when we convert using dimensional analysis, we're going to only pay attention, I will only pay attention to the length measurement first. Let's get out of miles. So I'm going to start with just miles. I'm completely ignoring hours for now. There are lots of ways to do this. This is just my particular method. I'm going to do this in 2 steps. I'm going to first go to kilometers because this is a conversion that I know from running 5Ks and things like that. 1 mile is 1.6 kilometers. So that gets rid of the mile. Now I'm in kilometers. And then just one more step here to go from kilometers to meters. There are 1,000 meters in every 1 kilometer. Now, my length part of this conversion is done. This is now meters per hour, and I could get a new number for that. Now we can address the hours. Hours is on bottom here, so to get rid of it now, I have to put it on top, and they will cancel. You could go to minutes first here if you choose. Doing this for a long time, I now have memorized how many seconds are in an hour. So I know it's 3,600. So now my units will work out, and I'm going to simplify this down and rounding to sig figs, 33 meters per second. Okay, so that's the idea. Why don't you hit pause, read example 2, and try to set it up. And then when you're done, hit play, and I'll work through it with you. So we have the density of gold at 19.3 kilograms per liter. And we want to convert that to something English, pounds per gallons. Again, we can only deal with one unit at a time. I'm going to turn kilograms into pounds. Both of those measure mass. So kilograms must go on bottom. And I do it this way because this is what I know off the top of my head, that a kilogram is bigger and that there are 2.2 pounds in every kilogram. All right, that takes care of it. Then to go from liters to gallons is tricky. Liters is metric, gallons is imperial. So I'm going to go from liters to quarts. In the real world, those two measurements are pretty close. I mean, they are really close. So you could approximate, let's say if you're in the grocery store, you could approximate and say that they are equal. In science, when you do measurements, that's not really good enough. So we know that 1 liter is slightly smaller than a quart, so 1.057 quarts in a liter. And then one more step and we'll be done. I know that there are 4 quarts in every gallon. So you do the math, and you will find that the density of gold is 161 pounds per gallon. Okay, in class we're going to take this up to a little bit harder level. If you don't understand what we're doing here, come see me before the class and we'll get you caught up.